So Ex should be what? The x component of the electric field is going to be just, so first let's write for R equals to capital R. The x component is going to be what? Q over 4 pi epsilon naught 1 over R squared times the coefficient of the unit vector x, which is going to be sine of theta cosine of phi. All right, you agree? And the y component, dy, that's going to be q over 4 pi epsilon naught 1 over R squared times that. That's going to be sine of theta cos the sine of phi. And then Ez is going to be q over 4 pi epsilon naught 1 over R squared times cosine of theta. So the next step then is to find the components of the Maxwell stress tensor. So you find these, that, all of that. But you can see that this matrix is going to be a symmetric matrix. So all we have to find is this, and that. The rest is going to be the same. This is going to be, for example, the same as this one. All right? So let's find those elements. Ex. That's going to be q over 4 pi epsilon naught 1 over R squared of sine of theta cosine sine of theta squared cosine of phi squared. All right, and Ex Ey is going to be q over 4 pi epsilon naught 1 over R squared whole squared Ex times Ey, this times by this. So that's going to be sine squared of theta, sine of phi, cosine of phi. And Ex Ez is going to be q over 4 pi epsilon naught 1 over R squared. So Ex Ez. So that's going to be sine of theta, cosine of theta, sine of phi. So we found these three. So all I have to find is this and this. So you can say that this is the same as, this one should be the same as what? Ey, Ex, and this is the same as Ez, Ex. So let's find Ey, that's going to be this with itself, so that's going to be q over 4 pi epsilon naught 1 over R squared. The whole squared times sine squared of theta, sine squared of phi. And what else? So when found this, I have to find Ey, easy, right? So that's going to be Ey easy equals to q over 4 pi epsilon naught 1 over R squared, the whole squared. So Ey easy, so that's going to be sine of theta, cosine of theta, sine of phi. All right, so now we found all the elements. So that means we determined basically E squared. How do you express E squared? What the E squared is just the magnitude of the electric field squared, right? So E squared is just simply this squared, right? The magnitude of this. So that's going to be the magnitude of Q over 4 pi epsilon naught 1 over R squared. You make the R squared. So the magnitude of the unit vector, which is 1, so you get Q over 4 pi epsilon naught 1 over R squared, the whole square. All right. So now we found the elements of all the elements for the Maxwell's stress tensor. The next thing that I need to find is dA. How do we define dA for the spherical surface, for the spherical part? Not for the plane. That's the next step that we need to do. But dA, how can I express for the curved surface?
R squared sine theta.
R squared sine theta d theta dp and what should be the direction? R hat, yes. So it should have 3 components, and you need to find the 3 components. So this basically, from here, you can write dA, dA x component. That's going to be this times by the unit vector R x component. So what should be that? This one, right? So that would give you R squared sine of theta d theta d phi of the x component, which is sine theta squared, right? And theta squared times cosine of phi. Are you following me? Just the x component. You multiply this with the unit vector here. So that will give you the x component of the area vector. And when you multiply with this, you get the y component with that, the z component. So I can write dA y equals to R squared of this times by the y component, which is going to be a sine squared of theta d theta d phi sine of phi. And the z component of the area, dA z, should be R squared sine of theta cosine of theta d theta d phi. All right? So we found the 3 components of the area. We found all the elements of the Maxwell's stress tensor. So all we have to do first is to evaluate the dot product of these 2.